Good day everyone, and welcome to our presentation. Today we're diving into the fascinating world of text-to-image generation with our paper, GLIGEN, Open Set Grounded Text-to-Image Generation. We're challenging the status quo of existing models, introducing a novel approach that enhances controllability and versatility by conditioning on grounding inputs. Stay tuned as we unravel how GLIGEN outperforms existing models and opens up new possibilities in the field. Let's begin. The field of text-to-image generation has seen significant advancements with models like DALL-E and PaRTy. These models, however, primarily rely on text inputs, which can limit their controllability. For instance, conveying precise object locations or handling open-world settings can be challenging. Make a Scene attempts to address this by incorporating semantic maps, but it too is limited to a closed set of categories. This brings us to the crux of the problem. The current models lack versatility. They are unable to condition on inputs other than text, which restricts the expression of information and limits their adaptability. This is a significant hurdle in the path of progress in the field of text-to-image generation. Our research aims to address this gap and enhance the capabilities of these models. Our proposed solution, GLIGEN, is a significant leap forward in the field of text-to-image synthesis. It extends the capabilities of pre-existing text-to-image diffusion models by conditioning them on grounding inputs. This approach allows us to preserve the vast concept knowledge of the pre-trained model while enhancing its functionality. The technical brilliance of GLIGEN lies in its use of a gated mechanism. This mechanism injects grounding information into new trainable layers, thereby enabling the model to adapt and learn from the grounding inputs. The result is a model capable of open-world grounded text-to-image generation. It can take caption and bounding box inputs and generate images that accurately represent the text description within the specified spatial constraints. In essence, GLIGEN is a versatile tool that not only enhances the capabilities of pre-trained models, but also opens up new avenues for research in text-to-image synthesis. It's a promising direction for advancing this field and expanding the capabilities of pre-existing models in various applications. While text-to-image diffusion models have made significant strides, they do have some limitations. For one, they rely solely on text input, which can limit their controllability. This is because they lack the ability to precisely localize concepts due to their inability to use other input modalities. This means that expressing the exact location of an object using text alone can be quite challenging. Now, let's take a look at the GLIGEN model architecture, as illustrated in the figure. The text features are fed into each cross-attention layer. What's new here is the addition of a gated self-attention layer. This layer is designed to take in new conditional information, allowing the model to incorporate grounding inputs. This is a significant step forward in addressing the limitations of current models. While generative models have made significant strides, they often fall short due to being trained on task-specific datasets. This is in stark contrast to the recognition field, where models are built on large-scale image data. To address this, we introduced GLIGEN, a novel approach that builds upon existing pre-trained diffusion models. GLIGEN not only retains the text caption as input, but also enables other input modalities for better performance and controllability. This includes the use of bounding boxes for grounding concepts, grounding reference images, and grounding part keypoints, among others. This innovative approach allows us to leverage the vast knowledge of pre-trained models while enhancing their functionality and controllability. In our quest to enhance the capabilities of text-to-image diffusion models, we've taken a unique approach. We've preserved the vast concept knowledge of the pre-existing models by freezing their weights. This ensures that the model's original knowledge isn't lost as we introduce new capabilities. To add the new grounding controllability, we've introduced new trainable layers into the model. These layers are based on a gated transformer architecture, which allows us to inject new grounding inputs. This innovative approach enables the model to generate images not just from text, but also from grounding inputs, thereby increasing its versatility and controllability. In essence, we've built upon the strengths of existing models, while introducing new functionalities, creating a more powerful and adaptable text-to-image generation model. Our research introduces GLIGEN, a novel approach that extends the functionality of pre-trained text-to-image diffusion models. Unlike traditional models that rely solely on text input, GLIGEN is conditioned on grounding inputs, enhancing its controllability and versatility. The key innovation of GLIGEN lies in its ability to preserve the vast concept knowledge of the pre-trained model. We achieve this by freezing the model weights, ensuring that the original knowledge is not lost during the training process. But we don't stop there. We inject grounding information into new trainable layers using a gated mechanism. This allows GLIGEN to leverage the grounding inputs, enhancing its ability to generate images that are not only visually appealing, but also contextually accurate. In essence, GLIGEN represents a significant step forward in the field of text-to-image generation, offering a more flexible and powerful tool for researchers and practitioners alike. Our research aims to enhance the controllability and versatility of text-to-image diffusion models. We strive to enable these models to be conditioned on other input modalities apart from text, thereby increasing their applicability and precision. To tackle this problem, we build upon existing pre-trained diffusion models, leveraging their vast concept knowledge. We then endow these models with new conditional input modalities, such as bounding boxes for grounding concepts, grounding reference images, and grounding part keypoints. This is achieved through a gated mechanism that injects new grounding information into the model. This approach allows us to preserve the original concept knowledge of the pre-trained model while integrating new, valuable information. The result is a more flexible and controllable text-to-image generation model that can adapt to a variety of tasks and conditions. Our research introduces a novel method, GLIGEN, which enhances existing text-to-image diffusion models with a new grounding controllability. This is achieved through a gated mechanism that injects grounding information into new trainable layers. This design offers flexibility during the sampling process, leading to improved image quality and controllability. In terms of training, we utilized the COCO dataset, with the aim of grounding open-world vocabulary concepts. We employed a pre-trained text encoder to encode each phrase associated with each grounded entity. This approach allows us to preserve the vast concept knowledge of the pre-trained model while expanding its capabilities. In essence, GLIGEN is a significant step forward in the field of text-to-image generation, offering a more controlled and flexible approach to synthesizing realistic images based on complex language instructions. In our research, we've designed an experiment that studies grounded text-to-image generation with bounding boxes. This approach unifies object detection and grounding data formats for training, which significantly improves the model's generalization capabilities. Now, let's talk about the key improvements we've made. Our model's grounding ability can generalize to novel spatial configurations and concepts. This is a significant advancement in the field. Furthermore, our model's zero-shot performance on SOCO and LVIS has outperformed existing baselines. This demonstrates the effectiveness of our approach and its potential for further applications. In summary, our research proposes a novel method that enhances the capabilities of existing text-to-image diffusion models. leading to significant improvements in performance and generalization. Let's delve into the key results of our research. Our novel approach, GLIGEN, has shown remarkable zero-shot performance on KEKO and LVIS datasets, significantly surpassing existing supervised layout-to-image baselines. This is a testament to its ability to generate images based on text and bounding box inputs, demonstrating its versatility and controllability. But what makes GLIGEN truly stand out is its grounding ability. It's not just about generating images, it's about generating images that are grounded in reality. GLIGEN can adapt to novel spatial configurations and concepts, showcasing its robustness and adaptability. The figure you see here illustrates the grounding token construction process for the bounding box with text case. This is a key innovation of GLIGEN, where grounding information is injected into new trainable layers, enhancing the model's performance and capabilities. In essence, GLIGEN is not just a text-to-image model, it's a model that understands and interprets the world around it, making it a powerful tool for image generation. Diving into the technical results, we find some compelling implications. Firstly, GLIGEN's superior performance on the COCO and LVIS datasets underscores the effectiveness of integrating grounding inputs into text-to-image diffusion models. This is a significant stride forward in enhancing the controllability of these models. Secondly, GLIGEN's ability to adapt to novel spatial configurations and concepts broadens its applicability. It can be utilized in a wide array of real-world scenarios, making it a versatile tool in the field of image synthesis. Lastly, the success of GLIGEN highlights the potential of leveraging large pre-trained generative models for downstream tasks. This approach can lead to substantial improvements in performance and controllability, opening up new avenues for future research and applications. This is a promising direction for the advancement of text-to-image synthesis and the expansion of pre-trained models' capabilities. Let's delve into the heart of our research, GLIGEN. This is a groundbreaking approach to text-to-image diffusion models. What sets GLIGEN apart is its ability to condition on grounding inputs, extending its functionality beyond existing models. This enhancement not only increases the controllability of the model, but also its versatility in image generation. Now let's take a look at the figure on the screen. This demonstrates GLIGEN's remarkable ability to generalize to open-world concepts. It does this using only localization annotation from the COCO dataset. This is a testament to the model's adaptability and potential for wide-ranging applications. In conclusion, GLIGEN represents a significant step forward in the field of text-to-image diffusion models, offering enhanced controllability and versatility. It's a tool that opens up new possibilities for image generation, and we're excited to see where it will lead us next. Our approach, GLIGEN, respects the knowledge encapsulated in pre-existing models. We achieve this by freezing the weights of these pre-trained models and introducing new trainable layers. These layers are designed to incorporate grounding information through a gated mechanism, thereby enhancing the model's controllability. GLIGEN's performance is noteworthy. It demonstrates the ability to generate images from text in an open-world setting, with the added capability of grounding. This means it can handle novel spatial configurations and concepts, extending its applicability beyond what was seen during training. In terms of zero-shot performance, we tested GLIGEN on the COCO and LVIS datasets. The results were impressive, with GLIGEN significantly outperforming existing supervised layout-to-image baselines. This highlights the power of building upon large, pre-trained generative models for downstream tasks. In conclusion, GLIGEN represents a significant step forward in the field of text-to-image generation, offering enhanced controllability and superior performance. In conclusion, our research highlights the untapped potential of pre-trained generative models. By building upon these models for downstream tasks, we can achieve significant improvements. This is exemplified in our GLIGEN model, which leverages pre-trained text-to-image diffusion models and extends their functionality with grounding inputs. Furthermore, we introduced a gated mechanism that enhances the controllability of these models. This mechanism allows us to inject new grounding information into the model without disrupting the existing knowledge base. This results in a more flexible and controllable image generation process, capable of synthesizing novel localized concepts unobserved in training. In essence, our work paves the way for more advanced, controllable, and versatile text-to-image generation models. We hope our findings inspire further research in this exciting field. Thank you.